Today we will begin to examine limits analytically, which means that we're going to be using a table of values. And so our goal today is to find limits using tables. So if we look at example number 5, we are going to complete the table of values to determine the limit as x approaches 1 of x cubed minus 1 over x minus 1. And so what we want to do is plug these x values into the function f of x equals x cubed minus 1 over x minus 1 and get the corresponding y values. If you do that, it's 2.71, 2.97, 2.997. We know that this is undefined. At 1.001, it's 3.003, 3.03, and 3.31. So the x values are getting very close to 1 from both sides. And as we look at that, our y values are correspondingly seeming to approach 3. So we'll say that the limit is equal to 3. Here are the directions for how to do this on a TI-84. You can also use Desmos by creating a table. And if you have questions about that, please send me an email. What I do want to point out is how to interpret the values. So if the values do not converge, the limit may not exist. If the values are very, very large, the limit may go to infinity or negative infinity. And if the values are written in scientific notation, your answer is probably 0. So, looking at another example, we have the limit as x approaches 0 of the sine of x over x. And so we have our table of values using either Desmos or a calculator. We get 0.959, 0.998, 0.999, this is undefined, 0.999, 0.998, and 0.959. If we examine the graph, it looks something like that. And we can say that the limit as this function approaches 0 is equal to 1. For examples 5 and 6, I gave you a table and asked you to determine the limit. In example 5, you want to determine the limit as x approaches 6. So the correct notation is the limit as x approaches 6 of f of x equals, and then as we look at these values, when we approach from the left, we're getting close to 9, but when we approach from the right, we're getting very, very large. Since these are not approaching the same value, the limit does not converge and does not exist. Okay, this is different than in example number 6, where we want to determine the limit as x approaches 0. And this time we're going to look at it as x approaches 0 from the left and the limit as x approaches infinity. So we're going to have two different answers here. In the first one, we're looking at the limit as x approaches 0 from the left of this function h of x. So as we approach 0 from the left, we're looking at these values right here, and we can see that we go from negative 20 to negative 200. So we can assume that we're approaching negative infinity because we got very, very large very, very quickly. We also want to look at the limit as x approaches infinity of h of x. And again, be careful with your notation. This time we're looking at these values where we're going from 0 all the way up to a larger x value, and we can see that our y values are increasing dramatically, and so we're also going to negative infinity. For 7 through 10, you will make a table. You need a minimum of 6 values. Okay, so I'll give you an example of what one table looks like, whoops, and then have you practice the other 3 on your own. All right, so we'll have x and f of x. In this case, we're trying to get very close to 0. So I'll do negative 0.1, negative 0.01, negative 0.001. And then from the other side, 0.001, 0.01, and 0.1. When we plug in those values, we get 1.95, 1.99, 1.999, 2.000, 2.004. And so we can see that our limit is approaching 2. All right. So now go ahead and complete a table for the following 3 functions. Once you do that,
attention staff, excuse the...
Okay, then we'll fill in our y values. So for f of x, we'll get 0.544, 0.506, negative 0.827, 0.827, and negative 0.506. And we can see that the values are starting to oscillate between a positive and a negative. Because they're not approaching one value, this sign does not exist. All right, last 2 examples. So we have our table again, x, f of x. We'll fill in the same values because we're approaching 1 again, or we're approaching 0 again. And then for our y values, we have negative 1 on this side, 1 on that side. And again, because we're not approaching the same value from the left as from the right, our limit does not exist. Okay, and then last example. This time we're approaching 2, so we'll pick 0.9 or 1.9, 1.99, 0.999, 2.001, 2.01, and 2.1. And since this is a piecewise function, we look at the definition. It says that f of x equals 1 if x doesn't equal 2. So all of these values are 1, and our limit equals 1. All right, let me know if you have any questions.